This is Calculus 1, Lecture 11B, Optimization 1. It's the first lecture on optimization. My name is Scott Grizzard from the University of South Florida. Hello. Um, and so this is really the big application um, for this section. So last time we talked about the shapes of graphs, and we've been talking for a while about the fact that I can find mins and maxes on an interval. So by the extreme value theorem, if I have a function on a closed interval, I'll have an absolute min and an absolute max. And then by Fermat's stationary point theorem, the derivative will be zero or not exist. So I can find the minimum and maximum on a closed interval by, taking the derivative, setting it equal to zero, checking to make sure that there aren't any points where the derivative doesn't exist, and then throwing those things back in the original function. And this was the example of a problem like that, where we did such a thing, where we took the derivative, set it equal to zero, and then checked the two endpoints and the place where the derivative was zero. We found an absolute min, we found an absolute max. Well, we can use this technique to do kind of real world problems. So the big ideas are things cost something. So what we're going to wind up with is kind of a thing we want to optimize given some constraint. And the way you do this is you make one equation, you take the equations, you combine them into one equation, you identify what you're looking for, and then you find the global max or the min if you're trying to minimize on that interval. And you've already done this in peer leading. Peer leading 11 was part of this, and then problem set 12, and then lecture 12a will continue this theme. Okay, so let's look at an example problem. I want to build a fence to enclose some rectangular area. Fencing costs $10 per linear foot. I have a budget of $800. What's the largest rectangular area that can be enclosed for that budget? So I've got $10 a foot on each side. I list my variables sort of like I was doing a related rates problem. I've got an area, it's square feet. That's the thing I'm trying to optimize. I've got a length, I've got a width. Both of those move when you take the derivative, and I've got some fixed cost. So these are my equations. The area equals the length times width, and the cost is $10 for a foot for that one, $10 a foot for that one, $10 a foot for that one, and $10 times whatever that length is. So that gives me my 10L plus 10W plus 10L plus 10W, or 20L plus 20W. Then I look for my interesting values. So then I'm going to sub in here. I've got, if 800, which is my fixed cost, I sub that in because it doesn't move. And I'm going to wind up it with 80 equals 20L plus 20W. That's going to give me that W equals 40 minus L. So I'm going to take this and I sub it back into this equation. Okay. And that will give me the, if I take this and sub it into that equation, that gives me one equation with one unknown. So I have 40L minus L squared ends up being the equation for the area in terms of the length. So what I'm going to do now is I'm going to take the derivative and set it equal to zero. I want to optimize this. So I take the derivative and with respect to L, and I get 40 minus 2L, and I set that equal to zero. So I get 40 equals 2L, or I get L equals 20 feet. Okay. Now I need to check my endpoints. Well, my endpoints, right, if I spend all my money on length, I'll wind up with 40 length. Okay, because each L costs me 20, right, because I had to add both of those sides. If I expand L, I have to expand both this side and this side. So L, if I put all my money on this piece right here, okay, I divide by 20, I get 40. So that's my maximum. That's one endpoint. My other endpoint is to use no length, and it doesn't make any sense to have negative width or negative length. And so what I do is I check those endpoints. Just like I did before here, I sub those endpoints back in. So I have A equals the area when L equals 20, I'm going to get 400. The area when L equals 0 gives me 0 because I've got all length and no width. And the same thing happens here. If L equals 40, then I've got no width. Here I had no length, all width. Here I have all length, no width. Both of those end up with 0. So the maximum size of this thing is 400 square feet. So just like I did with the related rates problem, I'm just going to say what I mean. The maximum area is 400 square feet when L equals 20 and Y equals 20. And if we looked at this, if we did this in Excel, which would be one way of kind of thinking about this problem, right? Here's the money I spend on length. Here's the money I spend on width. Again, it's 20 divided by however much money however much money I spend divided by 20. And this is my total area if I decide to spend. So if I spent 100 on length, I would be spending 700 on width. And that would give me a length of 5, a width of 35. That would give me a maximum area of 175. But if I have them be even in this case, now that's because the prices are even. If the prices aren't even, these aren't going to be even. This would be 20, and 20 would be my optimum right there. So I would be spending $400 on length and $400 on width, half my money. Okay. So that's the basic form of these problems. Now suppose, let's do another example. And that one I had nice endpoints. But what about this? Suppose the problem instead read that I want a rectangular fence enclosing 400 square feet. What is the least amount of money it will cost me? Now, part of this is going to be the same. I'm going to take the equations. I'm going to figure out what's going on with my variables. And then I'm going to solve the two equations for one unknown. But the difference is going to come in the endpoints. So let me show you what I mean. Okay, so that's my setup. It's basically the same setup I had before, except now area is fixed and C is optimized. So like before, I'm going to take my two equations and I'm going to find unknown. Well, this time right here, I'm solving for this one. Here, I solved for W and subbed in to get everything in terms of L. I'll do the same thing here. And since I know I'm about to take the derivative, I'm just going to put it in power form. Okay, so now what I'm going to do is I'm going to take the derivative and set it equal to 0. So I applied the power rule to this thing. This L just becomes a 20, and this thing here becomes 20 times 400. Those are just constants. And now I've got an L. I had an L to the -1. I pulled that in front, and I went down 1, and I have an L to the -2. I add this term to both sides, and now you can see why I left that 20 unevaluated, because it's going to cancel right there. This side becomes 1. This side becomes 400. Now I'm going to multiply L squared by both sides. I don't need plus or minus, right? Plus or minus is not needed because I've got -20 feet makes no sense. So it's 20. Okay, well, so that's the interesting X value. But notice something about these endpoints. I don't really have them. Well, I mean, there's 0 in one direction and infinity in the other. Let me show you why. So here's the same thing I did again, but now my area is fixed, and what I'm trying to minimize is the width. Well, watch what happens here if I do 0. And I copy all these up. Here, I would wind up dividing by 0, which we can see in the equation. So my endpoints for L are not hard. It's 0, infinity, with soft endpoints. So I don't have, I can't use the extreme value theorem here in order to say something, right? Because I'm shooting off to infinity. Here, I could use an infinite amount of, well, almost infinite, right? I could make this a really, really small number. And it's going to cost me a whole lot of money to build this little wall. If I can't actually spend 0, but I could just spend a very little bit on the length. Likewise, I could go up here. I could do 1,000 as the length, and I'll still wind up with a $20,008 wall, with an area fixed at 400. So either way, I don't have hard endpoints. That's the point. So I need some other way to show that this is a minimum. And the answer for that in this case is I'm going to use the second derivative test. So I take the derivative of my derivative. Now this -2 here, that -2 is going to multiply by that -1. So I'm going to wind up with a plus 2 times 20 times 400 times L to the -3. And notice here, if L is greater than 0, this number here is positive. So since the function is concave up when L is positive, I found the minimum. Okay. And that's basically what I do when I can't use the endpoints. So on the first one, I could use the endpoints because it was just, the L was restricted between 0 and 40. But here, because I've got with hard endpoints, but here I've got soft endpoints, right? This is not inclusive of the endpoints. So I can't use the extreme value theorem to guarantee I've checked everything. So I have to use some other argument. And the other argument I use is that I use the second derivative test here to show that it's concave up. I could have used the first derivative test as well, but I decided on the second. Now I just finished my thing. Oh, I forgot to calculate what the wall will actually cost. So that's the final answer. So remember, I wanted to check to make what's the least amount of money it will cost me, $800. Okay. So that's how you do minimization. And again, I could have set it up just like I did with the increasing and decreasing. Okay, so here, C of 1, I could throw in another number here. So if I throw in, let's see, where's my derivative again? Here it is. So my derivative, so if L equaled 1, I would have 20 minus, well, this big number here. That would be some big number over 1. Okay. So if I had some big number over 1, that's going to be less than 0. It's 20 times 400. But the point is, it's big and it's less than 0. So this right here is negative. That means I was decreasing on that side. And then let's pick a number in here. Let's pick 30. And the point is here, I'm going to, that should be 20. This 30 squared is going to dominate the equation. And I'm going to wind up with something greater than 0. So 80 over 9 is less than 20. It's slightly less than 10. So we wind up here with something that's greater than 0 because this term right here is less than 10. So we go up because we've got a positive. So I could have done a first derivative test to do that. I decided that I didn't want to calculate a bunch of numbers. I just did a second derivative test. But either one would have worked. Okay, let's look at another one of these, just a slightly fun one. So let's say that Democrats and Republicans and Democrats are both creating campaign commercials that produce benefits to society according to the formula BS equals R to the 1/3 D to the 1/3. R denoting minutes of Republican propaganda, D being minutes of Democratic propaganda. If it costs Republicans $1 million to produce a minimum of campaign propaganda, and Democrats pay $2 million per minute, how much BS can we have for $400 million? Not a lot these days, apparently, but let's go ahead and compute it. So what I'm going to do is basically what I did before. Okay, so my BS optimize doesn't really have units. R is in terms of that moves. D moves. Budget is C is fixed. Okay, and then I have an equation for BS. And I have an equation for costs. So it's going to be my costs are 1 times R plus 2 times D, and that's going to equal 400. And what we want to do is we want to maximize the amount of BS we can get for that 400 million. Okay. Well, we're going to solve for one of these. And then I'm going to sub this into my original equation. Now, because both of these are to the 1/3, I actually could do a little bit of multiplication here. But I'm just going to leave this as it is for the moment. I could do some sliding. I could do, because the exponent's the same, I actually could manipulate this. But let's just leave it for like it is. Okay. Now what I'm going to do is I'm going to use the product rule. I'm going to take the derivative and set it equal to 0. This derivative right here is going to have a chain rule. Okay, so that's fun. Now notice that this term here has a negative. So what I'm going to do is I'm going to add it to both sides of the equation. So this term is going to be negative 2/3 here. Well, they're both equal to 0. So what I'm going to do is I'm going to ditch the 1/3, and then I'm going to move this piece over there. So I just multiply the whole thing by 3 to get rid of the 1/3. And then I'm going to add this term to that side. That term should be on the bottom when we multiply it over. So let's just do that. The negative became a positive because I added it over to the other side. Okay, so now what I have is these two equations here. Well, the math actually is going to look a lot better than you think, because I'm going to multiply both sides by d to the 1/3 by 2/3. I'm going to multiply both sides by that equation. Okay, then I add 2d to both sides, and I divide through by 4. And I solve it. So this looked hideous, but because these things... And one of the things you're going to find is that when your exponents look like this, you're actually, when they're less than 1, you're actually going to wind up with math that's going to look a lot like this when you take the derivative. So they work out nicely. Okay. So now I've got 100 equals d here. That's interesting. Now, I could do a second derivative test again, but look at that derivative. Do I really want to do a second derivative on that? No. But this thing has endpoints, right? I'm trying to maximize here. That means I could spend 0 on D and get 0 BS. Likewise, I could spend all the money on D and spend 0 on R and get 0 BS. So what would it look like if I spent 0 on R? So for 400 million, the Democrats can buy 200 campaign minutes. So my two endpoints are D equals, in other words, D is in, and then when BS, when D equals 100, this right here, I do a little computation here. And 200 times 100 to the 1/3 is going to be... That's about 27.144. Okay. So that's the basic idea of optimization problems. I solve for one equation, take the derivative and set it equal to 0, find those things, and then make some justification on that I found the maximum and a minimum. Okay. So I make one equation. I kind of draw out some picture, make sure I'm doing it right. Make one equation, solve for where the derivative is 0 or the derivative doesn't exist, and then make some argument that I found what I was looking for, either a max or a min. Okay. Next time, we're going to talk about the economic implications, and we're going to look at another way to do these problems that's more like related rates was. And that's it for today.